In this lecture, we use the definition of an infinite limit to show that the limit as x approaches 0 of the fraction x plus 1 over x squared is infinity. Before we get started with the proof, let us re-examine the definition of an infinite limit. We say that the limit of f of x as x approaches a is infinity if and only if for every capital N greater than 0, there exists delta greater than 0 such that f of x is greater than n if or whenever 0 is less than the absolute value of x minus a is less than delta. F of x is equal to x plus 1 over x squared. A is equal to 0. The definition also mentions two positive numbers. The first is capital N, and the other one is delta. The relationship between capital N and delta is such that if or whenever 0 is less than the absolute value of x minus a is less than delta, then f of x is greater than n. Even though the inequality involving capital N is the conclusion, we start the proof with the n inequality. We start with the inequality x plus 1 over x squared is greater than n. Our objective is to arrive at the delta inequality. 0 is less than the absolute value of x minus a is less than delta. And since a is 0, we should get 0 is less than the absolute value of x is less than delta. We must show the existence of delta. We can achieve this by finding delta in terms of n. We need to get the absolute value of x in the delta inequality. And we observe that we have x squared in the n inequality. The square root of x squared is the absolute value of x. If we are to take square roots in the n inequality, then we will have to take the square root of x plus 1, which can be problematic because x plus 1 can be negative. And so we confine our search for delta around x equals a, or around x equals 0. Right now we are making a guess at delta. Let us try going half a unit to the right of 0 and half a unit to the left of 0. And so we are restricting x to be between minus 1/2 and 1/2. And so our first guess for the value of delta is 1/2. Because we need to get a handle on x plus 1, we add 1 to each part of the inequality. We get half is less than x plus 1 is less than 3/2. Now that we have ensured that x plus 1 is positive, we take the square root of each part of this inequality. The square root of 1/2 is less than the square root of x plus 1 is less than the square root of 3/2. We take the reciprocal of each part of this inequality and get the square root of 2 is greater than 1 divided by the square root of x plus 1 is greater than the square root of 2/3. We next multiply each part of the inequality by the absolute value of x. Multiplying the inequality by the absolute value of x can be problematic. We must make sure that x is not equal to 0 so that the absolute value of x is positive. Multiplying by 0 results in a useless equation. each part becomes 0, and we get 0 equals 0 equals 0. However, for the problem, x is approaching 0. X is not equal to 0. X is simply approaching 0. And so the absolute value of x is greater than 0. And the inequalities stay pointing in the same direction upon multiplication by the absolute value of x. Since everything is staying positive, the left part of the inequality gives us the absolute value of x times the square root of 2 is greater than the absolute value of x divided by the square root of x plus 1. Observe that the absolute value of x divided by the square root of x plus 1 is the same as the reciprocal of the square root of the left part of the original n inequality. And so to ensure the original n inequality, we take the square root of n, take its reciprocal, and set it greater than the absolute value of x times the square root of 2. With x between minus 1/2 and 1/2, this last inequality will guarantee that the original n inequality is true. It also means that 1 divided by the square root of 2 times n is bigger than the absolute value of x. So now we have two bounds for the absolute value of x. These are our candidates for delta. The first is 1/2. And the second is 1 divided by the square root of 2 times n. To make this all work, we choose delta to be the minimum between 1/2 and 1 divided by the square root of 2 times n. This means that the absolute value of x is less than 1/2. And it is also less than 1 divided by the square root of 2 times n. When the absolute value of x is less than 1/2, we already know that the square root of 1/2 is less than the square root of x plus 1 is less than the square root of 3/2. The absolute value of x being less than 1 divided by the square root of 2n implies that the absolute value of x times the square root of 2 is less than 1 divided by the square root of n. We then take the reciprocal of each part in the first inequality and then multiply by the absolute value of x. The result is the absolute value of x times the square root of 2 is greater than the absolute value of x over the square root of x plus 1. And since 1 over the square root of n is greater than the absolute value of x times the square root of 2, by transitivity we have 1 divided by the square root of n is greater than the absolute value of x divided by the square root of x plus 1. We square everything in this last inequality and take reciprocals. We get n is less than x plus 1 over x squared. This is equivalent to the original n inequality, and so we have shown that the limit as x approaches 0 of x plus 1 over x squared is infinity.